Hello and welcome to my class. I'm Grolin Annalisi from ThinkMO Education. I'm currently a Cisco Technology lecturer. If you like my video, welcome to my study group. Or contact my teaching assistant. WhatsApp account is +6 583444290. Today's topic is EIGRP experiments and OSPF. In the last lesson we learned some configuration. We are done with the announcement of EIGRP. Then finally let R1 learn the root of R4. In the last class, I let everyone observe. How many roots can R1 go to 4.4.4.4 now? We also talked about topology tables and routing tables, etc. If now there are 2 roots to go, will these 2 lines appear in the topology table? If it does not appear in the table, what is the reason? I also leave a question for you to think about. That is, if I want the following line also appear in the topology table, what should I do? Here are some small questions I left for you in the last class. So let's go through them together in this lesson. Before class, I configured the address. First review the final configuration content of the last lesson. I redeclare. And then go on. Because it's been a week since the last class, I think you may have forgotten these configurations. So do a review. Otherwise, I'm worried that you won't understand what I'm going to say next, including OSPF that will be discussed in the second half of the class. It is similar to the configuration of EIGRP. All configuration commands are similar. Everyone can feel it too. Okay. We officially start class. First here on R1. Create an as number in EIGRP. That is, I will now enter router EIGRP. Here is an as number. We still use 100. In the last lesson we used 100. Enter the routing view of EIGRP. To turn off automatic summarization afterwards. Then we now, after creating the entire EIGRP autonomous system, we're about to start building neighbors. The way to create neighbors is, for example, declare the directly connected network segment between R1 and R2. Then they establish a neighbor relationship with each other. Network 12.1.1.0. Then the directly connected network segment between R1 and R3 should also be declared. Is 13.1.1.0. Okay. This is the R1 devices. So now that we're done announcing, if now behind R1, there are other network segment information, I can also complete the declaration. But now R1 only has 2 direct connections. So the configuration of R1 is done. Let's look at R2 next. R2 is the same. I go inside R2. Be sure to create EIGRP first. Also 100. Turn off automatic summarization after. Also complete the declaration. Declare a direct connection between R2 and R1. Network 12.1.1.0. 0.0.0.255. It reminds us, I have now found a neighbor. That is 12.1.1.1 of the other party. We have seen. Then we configure the next. We will also declare the directly connected network segments of R2 and R4. 24.1.1.0. This is the configuration of R2. Then R3 is the same. Let's do it simply. The first must be to create EIGRP 100. Then network 24.1.1.0. 34.1.1.0. This is the configuration of R3. Oh, I made a mistake. It should be this device. Then I need to reconfigure again. I thought it was configured with R4. I now want to cancel the two announcements just now. One is 24.1.1.0. But 34.1.1.0 does not need to be cancelled. Because R3 itself has this network segment. Then we have to redeclare 12.1.1.0, 0.0.0.255. This is the configuration of R3. Next is R4. First of all the same. EIGRP 100. Then you have to manually turn off the automatic summarization. Network 24.1.1.0. This is the directly connected network segment. Between R4 and R2. Then it is the directly connected network segment. Between R4 and R3. 0.0.0.255. Okay. We are done now. For R4. There is also a loopback port. We're going to declare the loopback port as well. Let R1, R2, and R3 all learn. Network 4.4.4.4. This is the last one. 0.0.0.0. Okay. We are done. We can come to R4 now. After finishing R4. Let's focus on R1. First let's look at the neighbor table. In the last class, we talked about 3 tables. They are more critical. We are now here at R1. Check to see if it has learned the root 4.4.4.4. Show IP EIGRP neighbors. For now. Let's first look at the neighbors. How many neighbors will there be now? The neighbors of R1 and R3 are not established now. Let's also check here in R2. Show IP EIGRP neighbors. R2 is correct here. Why is R3 not established here? Let's check. (34.1.1.4). It should be that the address configuration of R3 is wrong. Some addresses I assigned before class. I need to check. The left interface of R3 is S10. 13.1.1.3. No problem. The right interface is 34.1.1.3. No problem. I don't seem to have announced it on R3. Then I declare here. Network 13.1.1.0. 0.0.0.255. I'm done now. It pops up a log. I'll recheck it here. Show IP EIGRP neighbors. Already learned. When it now learns, we should see the same effect on R1. That is, if we look at it now on R1, will be 2. After checking now, let's interpret this representation. For R1. Now we are looking at a neighbor table. Well, I told you before. This is the address of the interface that R1 sees locally. That is, this is when it and the peer are establishing. Peer interface address. So R1 local is 0.1. So, this 0.3 represents R3. This 0.2 represents R2. This is the relationship between them. This table, as we said before. So I don't talk about this watch anymore in class. Today I will focus on the topology table of EIGRP. Let's take a look at its topology table. In this table, let's just focus on 4.4.4.4. Everyone can see. In the entire topology table, it seems that there is only one address for the next hop. 12.1.1.2. Actually, R1 goes to 4.4.4.4. Both the upper and lower roots are available. But now in this topology table. But only one. So what is the reason? I told you before. There is another command. Add all links behind. Then this is not a real topology table. If you suffix this command with all links, it will show all physical connection table now. That is, as long as there is a way to go, it can show up here. So let's check out all links. Let me zoom in on it. Everyone can see. Above is a topology table. Below is the topology physical connection table. The difference between them is that if R1 now goes to the root 4.4.4.4, there is only one next hop in the topology table, 12.1.1.2. But in the physical connection table there are two. One takes R2. One takes R3. Then the question we think about is, if now the following line does not appear in the topology table, how do we put this line also into the topology table? Let's study this problem together. Only one root is displayed in the topology table. Then the root below is not included. We mentioned a thing last class. Feasible condition. Not all links will be put into the topology table. If you want to enter the topology table, feasible conditions must be met. Feasible conditions are what we call backup lines. AD. The advertised distance. It should be greater than the FD of the main line. For now, it will appear in the topology table if it meets the feasible conditions. It doesn't show up now. Certainly it does not satisfy the feasible condition. We judge whether it satisfies the feasible condition by looking at this parameter. Everyone please pay attention. Now there are two parameters in each parenthesis. The front one is FD. The latter is AD. So now for the main line. Its FD is 435/200. This is the FD of the main line in the feasible condition. So now the AD of the backup line is here. We want the lower line to be the backup line. So this is its AD. It is 297,856. This is the AD of the alternate line in the feasible condition. Then logically speaking, the feasible condition should be that the AD of the backup line is smaller than the FD of the main line. But now, obviously it doesn't satisfy the condition. So we have no way to add it to the topology table now. That's why it doesn't show up in the topology table. Because it does not satisfy the feasible condition. Then R3 cannot be a feasible successor router. It has only one way to go. We found out now. If it is not in the topology table, then according to what we said in the last class, it is impossible to achieve second-level switching. If there is a problem with the upper line now, since it is not in the topology table, EIGRP is to be recalculated. The line will be recalculated. Then go down the line. It can't be achieved. As long as there is a problem with the upper line, the lower line is switched immediately. It can't be done. So how to change R3 to the successor router of R1? What we're talking about is the AD of the backup line. That actually. Now this is a backup line. This is its AD. Remember the concept of AD? Advertised distance. That is the distance from the successor router to the target network. So it's actually this paragraph. If now I'm going to see the FD of the main line. Feasible distance from R1 to target network 4.4.4.4. That is. Below is actually this paragraph. The above is actually this paragraph. So we want to make the distance below this section smaller. The distance above is greater. As long as I change the value of this section to be smaller than the value of the above section. That's it. In this way, the feasible condition can be satisfied. This place we just saw. If I remember correctly, it should be 435,200. This is its value. This is 2297856. In short, I want to change the value below to something smaller. Then the value above can satisfy the feasible condition. Then we will modify it next. Then the first thing to change must be its metric. How is it modified? How did the metric come from? It is based on these 5 parameters. But usually, we seem to only change bandwidth and latency. We only refer to these 2. And everyone can see. There is a formula under it. This formula is the daily calculation method of metric. 256 times 10 to the 7th power. Divide by the link minimum interface bandwidth. Plus the sum of link delays. Divide by 10. This formula is a bit more complicated. It's okay. Let's do a calculation on it later. After the calculation is completed, we can know how this parameter is obtained. Let's calculate this number. Like the 435200 we just saw. Then let's study. What is the minimum link bandwidth? Let's look at this picture. Let's do the math first. R1 reaches 4.4.4.4. How is the 435200 of the main path calculated? Then before we calculate, everyone should know. How did this route come through? There is a 4.4.4.4 route here. Then if you want R1 to learn it in the end, what is its transmission direction? First of all, it needs to be transmitted to R4 through this loopback port. It must be an interface of the local. It is equivalent to passing through this interface. Through the local loopback port. This is a hop count. Then pass it to R2 here. The interface of R2 also received this route. So actually, it also goes through the E01 interface of R2. After a loopback 0 here. Passed an E01 here. Go down and pass an E00 here. That is 4.4.4.4 first enter R4 from the loopback port. Come out from the 00 interface of R4. The E01 interface passed to R2 enters R2. Then come out from the E00 interface of R2. Pass to the E00 interface of R1. This is called routing transfer. Then all the messages passed. They are all transmitted through the update message we mentioned earlier. Don't forget this. And I told you before. Transfer of routes and transfer of business traffic. Actually it's 2 different things. For example, I'm going to ping 4.4.4.4 from R1. This is business traffic. But what we're talking about today is the delivery of the route. So what does the link minimum interface bandwidth mean? Actually, it means now this route passes in the direction, the one with the smallest bandwidth, of the incoming interface of all devices. What everyone understands may be a sum. Not so. It's the smallest one. Then I ask you a question now. Now in the routing pass direction, how many incoming interfaces are there? Okay. There are 3. They are the loopback ports on this device. This interface. And this interface. So the minimum interface bandwidth of this link. It is the inbound direction of routing transmission. The one with the smallest interface bandwidth. So we will compare the 3 interfaces. Which interface has the smallest bandwidth? Then we need to look at the bandwidth of these 3 interfaces separately. First let's look at R4. Just check the information of loopback 0 here. Show interface loopback 0. Let's take a look at some of its details. Here we can see its bandwidth. Bandwidth is called BW. This is for R4. I'll take a screenshot of it and put it here. We'll make a comparison later. Then after watching our 4, we have to watch our 2.0.1 interface of our 2. So we go into our 2 here. Show interface E01. Then we can take a screenshot here. Let's see its bandwidth. Its bandwidth is relatively small. Only 10,000. Actually, it doesn't matter if we watch our 1 or not. Because the essence of our 1 and our 2 is the same. Because the interface is the default interface. We did not configure anything. But let's see. Left is 00. Check it out. Here we also take a screenshot of it. See here that the bandwidth is 10,000. So far we have identified all 3 interfaces. This is the far left. This is for our 2. This is the loopback port of our 4. Then please. What is the minimum link bandwidth now? It's here. Is 8 million. We compare the 3 interfaces separately. The 2 on the left are definitely smaller. So the minimum bandwidth is now 10,000. In a moment, we can directly bring it into the formula to calculate. Next we look at the next parameter. Sum of link delays. When data is being transferred. Loopback. Physical interface. Physical interface. These 3 interfaces. Then it refers to this 4.4.4.4 route. Come in through this loopback. Go to our 4. Then all these. In the direction of transmission. The sum of the delays of the incoming interfaces of all devices. Delay in this position. It's the DLY behind. 4R4. It's 5,000 here. The right interfaces of R2 and R1 are both 1,000. It's called delay. Then the sum of the link delays is now. That is. The sum of the 3 interfaces now. Should be 7,000. So now the sum of the link delays is 7,000. Let's do the math. In fact, this formula has already been calculated. First divide 10 to the 7th power by 10 to the 4th power. It must be 10 to the 3rd power. This is 1,000. Then 7,000 divided by 10 is 700. 1,000 plus 700 is 1,700. Then multiply 1,700 by 256. Equal to 435,200. We've actually figured out the value now. This is the 435,200 we just saw. Let's go back to this picture. That means now. This line is actually 435,200. So let's now look at our needs. Make our 3 a viable successor router. Then it means that our 3 is now 4.4.4.4. This paragraph is less than 435,200. This value cannot be changed casually. We can use this formula. Let's see where it can be modified. The only variable parameters are these 2. Minimum interface bandwidth of the link. And the sum of link delays. We can change these 2 variables. If we wish to make this result smaller, I can increase the minimum interface bandwidth of this link. Because it is a divisor. The larger the value here, the calculated value is smaller. Second, this is a dividend. I make the link delay smaller. The total value becomes smaller. So we can actually increase the minimum interface bandwidth of the link and reduce the sum of link delays. These 2 values can be modified. And in EIGRP, we do make changes like this. Usually, if running EIGRP alone, you can modify it between the 2. In fact, just modify a logical parameter. It doesn't matter. It only affects route learning and selection via EIGRP. It does not affect the actual rate of the interface. When everyone understands the interface rate, always feel like I changed this. The interface speed is changed. Not like this. For example, By default this is a 10M interface. You change it to 1000 megabytes. It's not a gigabit port either. We just modify it logically. Affect its routing. But in fact, there is no way to really change the physical bandwidth of its interface throughout the NA phase. If we change, both parameters will be changed. EIGRP can interoperate with other routing protocols in the later stage. In the future, multiple protocols running on a network. If modified, we usually change the delay. But if only running EIGRP, then bandwidth and latency can be changed. Because sometimes if you change the bandwidth, may affect other agreements. So we usually change the delay. But if only EIGRP, both parameters can be changed. This is very common. Then when we modify, we can make it bigger. You can reduce the parameter on the right. But this is not casually changed, and does not need to calculate. We have a reference object and modifying. For now, R2 is called the successor router. Then the distance from R2 to 4.4.4.4. It must be less than the distance from R1 to 4.4.4.4. That is, as the main line, the advertised distance must be less than the feasible distance. We now want this paragraph to be smaller than this paragraph. The distance from R2 to 4.4.4.4 is smaller than the above paragraph. I hope now. The distance from R3 to 4.4.4.4 is also smaller than the above section. Then I just need put the distance from R3 to 4.4.4.4. Change to the same distance as R2 to 4.4.4.4. It can ensure that the distance from R3 to 4.4.4.4 is less than the distance from R1 to 4.4.4.4. We don't need to switch it accordingly. The reason why the serial port is used below. It's because I want this line to be the only one in this picture. Certainly. The lower part can also run the Ethernet port. It's okay. Now we actually rarely see such a network topology. Generally speaking, it can also be all Ethernet ports. This is more common. For now, I just need to ensure the distance from R3 to R4 equal to the distance from R2 to R4 is okay. Then we change it to R2. That is, now I put the bandwidth and delay in the right interface of R3. Change it to be exactly the same as the right interface of R2. Then their calculated AD is the same. These two paragraphs are actually equivalent relations. As long as the parameters of the two interfaces are consistent. In fact, their distance to 4.4.4.4 is the same. AD on the top is less than FD. The AD on the lower side is also smaller than the FD on the upper side. There is no problem. So let's first look at the bandwidth and latency of R2. Let's take a screenshot of it. This is the bandwidth and latency of the R2 write interface. Then we make a modification. We modified it on R3. Then I must go to the interface of R3 first. The right side of R3 is the S11 interface. After coming in, we are going to change the bandwidth. This value can be changed directly. We can enter a question mark to see. Okay. We can now directly change. Then just enter the value here. Change to 10,000. After changing, there is a delay here. Type a question mark after the delay. Let me emphasize. There is a tens written here. Is that it will multiply by 10 by default. So, if you want to change the delay here to 1000, then you can write a 100 here. If you write 1000, here it becomes 10,000. Because it will multiply by 10 by default. In some configuration parameters of many networks have similar concepts. So sometimes you need to pay attention. Let's just change it to 100 right here. Let's take a look when we're done. Show interface S11. Now we see this interface. It seems to be the same as before. Now the bandwidth is 10,000. The delay is also 1000. It is equivalent to changing the parameters of these two interfaces to be the same. If you look at the IP header later, in fact, there is a parameter in it that will be multiplied by default. That's not the point. Now these two interfaces, I changed it to the same. So let's look at the topology table on R1 now. See if there will be a change. Show IP EIGRP topology. Okay. Now let's look at the topology table. There are two lines in it. Because now the main line and the backup line, the two values become exactly the same. This can also be brought into the formula just now to calculate. At the beginning, it should be more than 2.29 million. Now it has been changed to more than 400,000. It's smaller than this 430,000. So it comes in now. The topology table does not add all links. It has appeared now. So when this comes up, let's check the IP routing table again. Now R1 goes to 4.4.4.4. First of all, let me take a look at the topological table. Check out all links. For now, the same goes for all links. So why doesn't it appear in the routing table? Let me check. In the routing table this is 4.4.4.4 going to 4.0.0.0. The second item of the next hop does not appear. It should be advertised that the distance is also equivalent. There is a problem with the configuration just now. Let's check the configuration just now. Show IP router. This is the topology table. Both of them are already in the topology table. The next hop is the serial interface. Okay. We should not look at the routing table. There is now only one entry in the routing table. Let's look at the topology table and it's okay. It now appears in the topology table. Well, the experiment is actually over. Everyone can demonstrate. I leave you with a thought question. For example, down the interface above. Then you can look at. I give a simple example. You can refer to it after class. I am now going to ping this 4.4.4.4 from R1. Suffix a repeat. After that, I down the above interface. Then let's take a look. When can it switch to the link below? That is to say, now through our artificial modification, the route below has become an alternate path. Because we already have it in the topology table. Let's ping it first. I teach you a command. For Cisco inside. It does not have a command called ping all the time. It must be suffixed with repeat. For example, I'm going to ping 4.4.4.4 now. It works. Then we will add a command like this later. How many suffixes do you want it to ping? Suppose we ping 10,000 times. Then we are in the process of ping. Let's advance to the R2 interface later. Left port of R2. E00. Let's shut it down later. Okay. We enter this interface. Interface E00. Then shut down. After the shutdown is completed, let's ping here first. Then see how many packets it drops. Then switch back. We start ping. Shut down. Let's observe. It drops a packet. Dropped 2 packets. Dropped 3 packets. Actually, it does not realize the real second machine switching. This is actually due to the problem of the current simulator. It is still different from the real machine. Okay. Press Ctrl+6 to turn it off. So now everyone can see. This link is actually down. Because this interface is actually down. After down, it is indeed switched now. But it does drop packets in the middle. About 6 packets were dropped in the middle. That actually puts it in the job. EIGRP is slightly faster than in the simulator. Relatively speaking, the presentation is a bit slow now. That is. These exclamation points above. In fact, it means that the line is going up. Then when the interface is down. After a discarded packet is generated in the middle. Its line quickly switched to the bottom. Everyone can observe the experimental phenomenon after class. Before you turn the link below into a backup line. Then do this. See how many packets are dropped in between. After that, you can follow what we said in today's class. Make it into a feasible successor router. That is R3. You turn it into an alternate line. Then you go down the interface of the above line. Observe how many packets are dropped. About 3 times that. Takes about this long. It needs to be recalculated when the packet is lost. I won't demonstrate in class. EIGRP is actually almost so much content. Finally, let me emphasize. After we artificially modified, we can take the original suboptimal path. Become a backup path. In order to achieve second-level switching. Keep business uninterrupted. Actually, the real chance is slightly faster than the simulator. And our modified delay. The one we modified is called the logical attribute. It is not a real physical property. That is, the bandwidth is actually generated according to the physical characteristics of the interface. You change an F port to 1000. It's not a gigabit port either. It's just that the command we wrote, only when calculating based on routing, will serve as a logical reference parameter, which then affects our calculations, which in turn affects routing. We talk less in the NA stage, because the overall dual algorithm will be covered in the NP phase. So these parameters mentioned in NA, you also need to understand the name. Next, let's talk about today's key points. OSPF. In the NA stage, we only learn 2 dynamic routing protocols. One is EIGRP. The other is OSPF. The full name of OSPF is Open Shortest Path First. It is also an interior gateway protocol. Remember what we said earlier about the concept of inside and outside? Okay. Refers to a dynamic routing protocol that runs in an AS. It is not the same as what we call EIGRP. Of course, EIGRP can now also be called an IGP protocol, because it is not running on the public network now. Here is a new word. Actually, we didn't mention this word when we talked about EIGRP. Link state. OSPF is an implementation of a link state routing protocol. What does link state mean? That is, whether it's the link state we're talking about, or advanced distance vector. They actually refer to the algorithm of the protocol. We mentioned RIP to you when we talked about EIGRP before. So now I will make a supplement for you.